All right, so let's go ahead and wrap up our semester by looking at some exponential applications. I'm going to forewarn you guys, I will be turning to a calculator here momentarily, and I'll be honest, I don't know how to bring up a calculator pad on my iPad in this application that I'm using. So I'll coach you along as much as I can. If not, we'll do some more demonstrations in class. But the first application, we're talking about population. Again, that's a classic situation where we're going to see an exponential model occurring. We're talking about the population of rainbow trout in a certain lake, and it's modeled by P of t, so my population with respect to time, it's equal to 150 times 1.9 and then 0.07 t power. All right, so it looks a little bit different than we have, but I'll break it down in a moment. T, the variable, is measured in months. And P of t, the function, is the measurement of the population. Now, some things are new, right? But if you strip this down, right, if I take this 150 away, and if you look at the 1.9, and let me just go ahead and write it to the x power, what I have is a growth model kind of in hiding. My a is greater than 1, so that's the one thing we want. And I know we have 0.07t, but since we're multiplying 0.072t, that's like having the exponent being an unknown. I would still have to figure out what that exponent is and then raise it to raise 1.9 to that power. So it's still behaving like that particular one. So what kind of model are we dealing with here? Well, it would be the growth model, right? Because the power that I have is positive, all right? So that's classic. So my a is greater than 1, and we're basically dealing with something to the a to the x. So we have a growth model. So if we were to model this, right, if we were to graph this, right, it'd basically have that shape. Something that is new that that maybe some of you have heard before, but I thought I would sneak at you guys. In mathematics or in science or whatever we're dealing with, when someone mentions an initial population, they're basically referencing when time equals to 0. Essentially, when this model starts, all right? So perhaps this model started, in a January or in a February, but whenever the scientists decided to start the model, that's the initial population. So essentially, t is equal to 0. So to find my initial population, right, I'm basically finding p of 0, and if I plug that in, right, 0.07 times 0 is 0, so we get 150 and 1.9 to the 0 power. Anything to the 0 power is 1, so we have 150 times 1, so we have 150. So according to this model, the population of the trout, when we started this model, is 150 trout. All right, so that's what that basically means in terms of that. When we now ask what's the population in 5 years, well, remember the time is measured in months. So the first thing I need to do is figure out that 5 years, right, is equivalent to 60 months, right? And the way that I basically did that, right, a year is basically has 12 months in it, giving me the 60. So we're basically looking for P of 60 as far as this mathematical model is concerned. All right, so we've got that going for us. And then we have 150, 1.9 to the 0.07 times 60. All right, and so here's where we obviously need a calculator at this point. I've got one off to the side here where I'm gonna, it's a TI-84. So let me just kind of coach you up. If you have a TI-84, you literally just type it the way it is. So I'm gonna show you on my input screen, I'm gonna have 150. I'm gonna open up a set of parentheses, put 1.9 in it, close it, and then I'm gonna use the little caret feature. And then in another parentheses, I'm going to put 0.007 times, the little dot, times 60. Let me make that a little cleaner. Let me reverse that. Right? Times, I'll put a little dot there, 60, and close parentheses. So that's what I'm basically putting in my calculator. So let me punch it in real quick. Right? So I got 150, open parentheses, 1.9, close parentheses, and then I'm going to raise this. So I'm going to use the little caret feature, right? I'm going to raise this to the 0.07 times 60. Okay. Lots of parentheses, so it's taking me a while to punch it into my calculator. All right, and so what I'm getting from that, right, as I'm getting roughly 2,222.57. So if we round that off, it looks like 2,223 trout. All right. So again, the best I can do, I apologize for this. I will get better at this. Unfortunately, I'm just not good at this right now. I'm new to the whole environment here. But basically, right, that's how, if you have a TI-84, this is how my whole line of these sequences. I write 150, parentheses, 1.9, close the parentheses, use a little caret, and then in another set of parentheses, I write the 0.07 times 60. Hit enter, and you get this answer, and there it is rounded off. So that's basically how we use this model. There's much more to this story, but I think for the homework and for the time frame that we are, I just want you to see an exponential model in action, look at some of the language, and then just do some evaluations and start using your calculators, because you will in your 151 classes, and it's about time that we started doing it as well. All right, so there is the exponential growth model, right? So there's number 3. Let me cut away, and we'll come back and do number 4 together. Talk to you soon.